what we have to do today, now we have to learn the empirical rule, Chebyshev theorem, box plots. Well, and in addition to these topics, we should learn sampling or sampling distributions. Well, the latter topic is the core of statistics, and if you understand the meaning of sampling distributions, you will understand the whole economic statistics well, and you will understand why we use certain tests, why we use statistical tables and other statistical tools to do quantitative research. Well, also today we should learn about Stata program. We should learn how to use Stata program, and our teaching assistants can help you to install this program and could solve maybe some problems if you have. Well, first let me share my screen and explain how to use empirical rule and Chebyshev theorem. By the way, in the next seminar, we will conduct a short quiz about empirical rule and Chebyshev theorem. Well, you have to be able to use them in practice. Well, so wait. Okay, first, 1 week ago, we learned measures of central tendency, measures of dispersion, their numbers. Well, 2 weeks ago, we learned frequency and relative frequency distribution. These tools are very important to generalize the data set. In addition to these rules, there is another interesting tool, and name of this tool is boxplot. Boxplot is very simple. Boxplot is a graphical display based on quartiles that help us picture a set of data. Well, and to construct boxplot, we have to calculate the first quartile, the median, highest, the second quartile, the third quartile, minimum and maximum value. I think all of you can easily find these numbers in a given data set. And next, we should make a chart like this. Well, this is an example of box plot. It could be horizontal, it could be vertical, so that doesn't matter. Well, and how to interpret a box plot? Imagine that we have a data set, and this data set reflects delivery time of pizza, well, within given time period. Well, and we use boxplot to describe this data set. We see that the median delivery time is close to 18 minutes. Well, this is the median. It is a line in the middle of our box. This is our box. Why we name this chart box plot? Well, this line is our first quartile. This line is our third quartile. We see that 25% of orders had been delivered within 15 minutes or less. Well, and we see that 75% of our orders had been delivered within 22 minutes or less. Well, also we see that minimum delivery time should be probably 13 minutes and maximum delivery time probably 30 minutes. Well, what also can we learn from this chart? We can learn whether there are outliers or extreme values in our data. Look, we see that, for example, in this chart, we see that minimum value is close to the third quartile, but maximum value is far from the third quartile. What does it mean? It means that our distribution is skewed. It means that, well, there are some large extreme values in our data set. And hence, if we rely on simple average in describing this data set, we have to be very careful with the interpretation, because this data is skewed, and probably median is better way to find a typical delivery time in this data set. Well, in Excel, it is fairly easy to construct a box plot. In Excel, we have a tool. If you click Insert, and if you click histogram, well, you can find box and whisker plot. This is box plot. Box and whisker plot is another name of box plot. And again, let me stress that methodology of making box plot can be a little bit different in different statistical packages, Excel and our textbook. In my lecture, I use the simplest way to make a box plot when we use minimum value, maximum value, and free quartiles. But in statistical package, by default, we often calculate, we often also use some points instead of minimum and maximum value to indicate large extreme values. And today, at the end of the lecture, we will try to make a box plot in Excel together. Well, next, in addition to box plot, well, we have another interesting indicator. It is a skewness. Well, skewness is calculated using such a formula, or in general way, the formula look like this. It is indicator. Well, and we use this formula to check whether our data follows normal distribution. Not follows normal distribution, whether our data is skewed or not skewed. And that's it. Well, how to check whether our data is skewed or not skewed? There is a benchmark value. Well, and this benchmark value is 0. If our data is different from 0, it means that the distribution is skewed. Well, so in principle, to check whether there is a skewness distribution, there are, I suppose, several ways. One way is to calculate skewness indicator, another way to compare mean and median. Well, you can also rely on box plot, or the simplest way, you can create a frequency distribution chart to check whether there is any obvious skewness in our data. Well, why we need to learn whether our data is skewed? We need to learn it to check whether we have to rely on median instead of the mean, or whether it doesn't matter. Well, what indicator is better to rely on? Well, so Chebyshev theorem. Chebyshev theorem is probably so here we learn just an intuition of the Chebyshev theorem, and we don't try to prove it, because proof of this theorem requires knowledge of advanced mathematics. Well, and it could be fairly difficult for management students. Well, first, we have stressed that small standard deviation for a set of values indicates that these values are located close to the mean. Well, and large standard deviation reveals that observations are widely scattered about the mean. Well, and there was Russian mathematician Chebyshev. He developed a theorem that allows us to determine the minimum proportion of the values that lie within a specified number of standard deviations of the mean. How it looks? Well, for example, according to Chebyshev theorem, at least 3 out of every 4, or 75% of the values, must lie between the means plus 2 standard deviations and the mean minus 2 standard deviation. I guess 75% of our data lie within plus minus 2 standard deviations from the mean. Well, and also from this theorem, we can using this theorem, we can state that 88.9% of our data should lie between plus minus 3 standard deviation from the mean, and at least 96% of our data should lie between plus and minus 5 standard deviation of the mean. Well, so in general form, in Chebyshev theorem, we apply such a formula 1 minus 1 divided by k squared. So for any set of observations, sample or population, the proportion of the values that lie within k standard deviation of the mean is at least so, and this formula. Well, and let me note that we cannot say something about plus minus 1 standard deviation from the mean, because in this case k should be equal 1 and this formula cannot be applicable. Well, hence we can just make a conclusion about 2 deviations from the mean, 3 or 4. Well, so that's it about Chebyshev theorem. How to apply Chebyshev theorem? First, you have just to remember these 3 bullet points. And next, you should keep in mind that we can apply Chebyshev theorem even if our distribution isn't bell-shaped, as it isn't number 1. Well, so how can we apply it in practice? For example, you have a continuous data and you want to know whether, for example, you have data of marks on economic statistics and you know distribution of these marks, and you want to learn probability. For example, you want to learn percentage of students who received marks within 2 plus minus 2 standard deviations from the mean and plus 2 standard deviations from the mean. Well, could be used. In addition to Chebyshev theorem, there is an empirical rule. It's just a rule and you have just to remember this bullet point or bullet points in your textbook. For symmetrical bell-shaped frequency distribution, approximately 68% of observations lie within plus and minus 1 standard deviation of the mean. Look, in empirical rule, we can draw conclusions where using 1 standard deviation of the mean. But in empirical rule, we have to be sure that our data follows a normal distribution, i.e. our data is bell-shaped. Well, next, the empirical rule states that about 95% of the observations will lie within plus and minus 2 standard deviations of the mean, and practically all 99.7% will lie within plus and minus 3 standard deviations of the mean. And in principle, that's it about empirical rule. Well, practical application, not to be honest, we rarely use empirical rule and Chebyshev theorem in practice, because when we work with statistics, we usually rely on charts, box plots, frequency distributions, or statistical tests instead of Chebyshev theorem to learn something about data, to generalize data set. But, well, if you want to make a very simple but not very precise impression about data set or insight about data set, so you can use both theorems. Well, for sure these topics are important, but there is more important topic in our today, and this topic is about introduction to confidence intervals. But first we have to learn a property of descriptive statistics. Well, imagine you want to calculate the mean of a variable. I am sure all of you can calculate simple averages, right? I can give you a data set and you can immediately apply average formula in Excel to calculate the mean. But how can one check the accuracy of these statistics? Well, is any way to check whether we have to trust our mean or whether our mean indeed reflects a typical value in our dataset? Well, we know that any statistical package, Excel, RStudio, Python, can easily calculate the average. But doesn't necessarily mean that we have to trust this number. No, we shouldn't trust any number we have, especially if this number can be calculated automatically. We have to think, we have to discuss whether it makes sense to trust this number. Well, and one could ask me, okay, but how do you examine whether the sample mean is fine, whether we have to trust sample mean? And in statistics, well, to check whether we have to trust our sample mean or other indicators, we rely on a simple logic. We should check whether sample mean is far from the population mean. Population mean is the most accurate number we can get from our data because it is population. Well, sample anyway, it is sample. We cannot, for example, if I survey 20 students in your course, randomly chosen, to find average GPA, I can find average, and this average can be fine. We can trust it, but if my sample is representative. But what if I'm unlucky? And what if I randomly choose students with high GPA only? Just because it is random choice. It is random choice, and because of small luck, I choose just students with high GPA. In this case, my average GPA should be too high than the population mean, than the true GPA. It could be another situation. I'm unlucky and I survey students with low GPA, and in this case, my low GPA for sure. We cannot trust my number, but my analysis, because I could underestimate GPA. Well, and my job as being a statistician is to find such a sample mean which should be close to the population mean. But how can we check whether it is close when we don't know the population mean or there is no way to calculate the population mean? Well, and to check it, we have to use some theoretical knowledge. Well, and today we should do one simple exercise in Excel to understand how this stuff works. First, we should learn a sampling error. Sampling error is very, very simple. Please don't read this slide. Look at this formula. Sampling error is a simple difference between my sample average and population average. Well, so sampling error occurs because the sample isn't a perfect representation of the population. It is apparent. Well, and moreover, sampling error increases when the sample size decreases. Well, when your survey, if you cover a lot of students in your survey, your sampling error will be small, and vice versa. Well, and now let's calculate a sampling error of the mean. Well, in your let me show you. Well, in MS Teams, go to Files, Teaching Materials, Lecture Files, and there is a file L4 Data for Students. Please open this file Please download and open this file in Excel. Type plus if you are ready. Type plus if you are ready. L4 file. Let's wait a couple of seconds. Because now we have to do, so I can explain using my slides, theories, but I think that you can read textbook. It's better to show how it works in practice in Excel. Well, and I think it is a better way to learn how so this works. It seems that so. Okay, let's start. What we have. First, you in column A, there are numbers. So it is a ID of each observation. I just numbered rows in my data set. Column B is the population data. It's a variable. We have some values inside this variable, and it is population data. Next we have many columns. Column sample 1, sample 2, sample 3, and so on. In total, we have 100 samples. These variables are binary. What does it mean? It means that in sample 1 is a survey. I surveyed first, second, third respondent. I didn't survey respondent 4, respondent 5, but I surveyed respondent 6. It's one sample of surveyed respondents. Sample 2 is another survey. In this survey, I interviewed third respondent, 6, 7, 11, but I didn't talk with respondent 1, respondent 2, respondent 4, respondent 5. Sample 3 means that I surveyed first, second, fourth, fifth, sixth respondents. I didn't survey third respondent, and so on. Well, what does it mean? It means that I have 100 surveys. All of these surveys rely on simple random sampling. Well, and we survey different persons, randomly chosen. Hence, our sampling, so our samples are different, but they could be representative because we rely on random sampling, simple random sampling. Well, what we have to do now? Now we have to calculate simple sampling error. How to calculate simple sampling error? I think it is fairly obvious for you. First, you have to calculate average, population mean average. Use B column, use our population data to calculate population. Let me show my file, it's better. Well, wait. Well, please calculate simple population average. This is the formula. Calculate it, please.
It's 5.8. Yeah, it's right. It's 5.80.
Ivan, I can hear you.
Oh no, it's nothing. I just compared your answer with mine.
5.18 should be. Okay. Next, let's calculate sample averages. To calculate sample average, we should apply average if formula. How to apply average if formula? First, we should use range. Our range is our binary values. Criteria is 1. 1 means that we surveyed person. And this one is our range from column B. Well, and here we calculate average of our output among surveyed respondents in sample 1. Please apply the same formula and the answer is 5.227. It should be like this. Check whether you have the same output. Type plus or say something if you are ready. Okay. Good, thank you. Well, next, please freeze column B and apply this formula for the rest columns. Calculate the same average if so conditional averages for all columns in our data set. Look, we have 100 values. And compare your numbers with mine. Type plus if you are ready. Okay, yeah, thank you. Thank you. Well, next. Um, so now we should calculate sampling error of the mean. Well, in our formula, it is difference between sample mean and population mean. Don't forget to freeze the population mean because it is the same for all differences. Wait. This is our difference and calculated for all values in our dataset. And calculate this difference for all sample averages. Type plus if you are ready. This is the formula. Are you ready? Okay, it seems so. Well, yeah. Why we use sampling error? We use sampling error to check whether we have to trust our sample averages. And what we have, look, in the first survey, our sample average is higher than population average. The same can be said about the second survey, but in the third survey, we see that our sample average is smaller than the population average, and so on. And if we look at our numbers, I'm sure that we won't find zeros. I used all sample averages are either higher or lower than population average. Well, what we have to do. Okay, we see that our numbers are either overestimated or underestimated. Doesn't mean that we shouldn't trust these 100 trials. No, we can trust if we learn one thing more. Well, what we have? We have 100 sample averages, right? What if we treat these 100 sample averages as a dataset itself? If this is a dataset, set of numbers, we can analyze this data, right? Let's try to analyze this data. Let's create a separate data set. Please use separate data set to check, well, to learn this thing. Well, no, let me show you how to, how to use this, how to create a separate data set using this means. Well, I hope that all of you remember. Let me show you another file. Maybe it's more convenient for you. Wait. Yeah. Well, look. Now let's create a data set. First, we have to name our rows. It is sample 1, 2, 3, 5, 7, and up to sample 100. Look, it is our first column. The second column should be full of our sample averages. You have to use transpose formula in Excel to transpose this row. To do this, and how to use this formula, you should select range. You should select 100 empty cells. Once you use 100 empty cells, you should type transpose, and next you should select your sample averages. Ctrl+Shift+right arrow to select the whole sample. And final thing, you should press Ctrl+Shift+Enter to fill all empty cells. Well, please use this formula and transpose our data. Type plus if you successfully transposed the data set. No, you shouldn't solve the selection, Ivan. Okay, good. I see you know Excel. Very good. Next, let's do a simple exercise. I hope all of you should make a small descriptive statistics. Very small descriptive statistics. Find minimum, maximum, mean, and standard deviation of your means. Please use this data set to find minimum, maximum, mean, and standard deviation. Get the same numbers. I'm sure that you are able to find them without my help now. Type plus if you are ready. Plus, I see plus. Should I wait a little? Say something.
Yeah, just a couple of more seconds.
Okay, yeah. Again, it is minimum, maximum, average, and standard deviation. And when we are waiting for the students, let me say something interesting. Look, our minimum and maximum for sure are different from the population mean. And the difference, by the way, could be even large, especially if your sample is small. Well, could be. If your sample is large, this difference should be small. Well, but what is interesting here that our mean is close to the population mean. The difference between population mean and mean of means is very, very small. Wow. Look, the difference just, we can say that it's almost nothing. What does it mean for us? And this fact means a lot. It means that all of these averages, all of our 100 averages are unbiased estimators. What does it mean? Unbiased estimated is a special term in statistics, and it means that the average of all possible values of sample statistic equals a parameter, no matter the value of the parameter. When we know that if, for example, we want to calculate average of something, and we know that if we repeat our survey 100 times, and if we calculate average of our averages, this output should be close to the population average. If this is true, we can say that our statistic or estimator in other name is unbiased. Well, and this is important. And our job as a statistician when we collect data to try to get unbiased estimators. And for example, if your sample isn't representative, for example, if you have a selection problem, imagine I conduct a survey of my clients. So I have a shop somewhere, I sell some food in this shop, and I conduct survey in the morning only. Well, for sure my survey will provide me with biased data because working population rarely visit food stores in the morning. Usually they visit them in the evening. Well, hence I can survey mostly retired persons, probably those who are unemployed, or those who on different type of leaves. Well, hence my survey is, it means that there is a selection problem, my survey cannot be representative well, and in this case I cannot get unbiased estimator because it is biased, so there is a selection problem. But if I rely on accurate sampling, probability or non-probability sampling, I can obtain unbiased estimator, robustly speaking. Oh, well, okay, you calculated average, but what about the distribution? You know from the last lecture and from the last seminars that sometimes it's a bad idea to work with average only. Sometimes it makes sense to calculate medians, quartiles, especially when our distribution is skewed. How can we check whether our distribution is skewed? There are different ways, and let's rely on the simplest one. Let's create a simple frequency distribution of our means. Well, my class width is 0.1. Well, and what you have to do now, you have to apply, wait. You have to create these two columns. Our starting point is 4.5. Look, next I add 0.1, and here I make a reference to this cell. Please create left and right column. Type plus if you are ready. Or say something if you need help. 4.5, 4.6.
Sorry, I have a question. Can you hear me?
Yeah.
I have a question. Why do we start from the 4.5 in the left column?
Because it's convenient. So I think that this point is convenient to start with. Well, 4.5 or 4.0. Well, you remember that our frequency distribution should be convenient for the reader. Well, and this is the reason why I use 4.5 and 0.1 class width.
Okay, thank you.
And 4.5, the most important, is smaller than our minimum value.
You mean the convenience is that we do not take 4.6, but we take 4.5?
Yeah.
So just more prettier.
Between 4.5 and 4.6, it is our first bin. We know that no values should fall, should be here. You can skip it, but I use it just for beauty.
But we could start from the minimum value, 4.6.
6?
Mm-hmm.
It's not a mistake. It's definitely not a mistake if you wish, and if you want to save your time.
Thank you.
C103. Yeah. Wait. Yeah. So, Finn, are you ready? So now we have to calculate values. So we have to create a frequency column. To do this, you should apply such a formula. Look, here I use bigger than and this operator. Apply the formula to calculate frequencies and check whether sum of your frequencies equals 100. Check yourself. Type plus if you are ready. What's the formula for right column? You mean this, Valeria? This is concatenate, just simple concatenation to create labels. If you wish, you can create concatenation column. Well, next, please create a frequency histogram. It should be like this. Let me put it on a separate worksheet to make it visible for everyone. Well, wait. This is our frequency distribution histogram. Please create it in Excel. Create this histogram and look what we have. Type plus if you are ready. Well, what we have? Look, first, our distribution looks like a bell-shaped distribution. There is no huge skewness in our distribution. Well, and also we see that most of our averages, sample averages, are concentrated around the population average. Population average is 5.18, and we see that most of our sample averages are around these numbers. This number. Well, and this fact is a good illustration that we work with unbiased estimator. And moreover, we see that a number of sample averages being different from our, being far from population average is small. We see that, for example, number of sample averages between 4.6 and 4.7 is really small, and the same can be said about this interval and this interval. Well, and once we move closer to the population average, we see that so bins are higher, meaning that more and more so sample averages are concentrated around the population one. Well, and this is a pretty important fact in statistics because it shows two things. First, it shows that any statistic, it could be average, standard deviation, median, proportion, is random. Any statistic which we derive using sample data can be different from the population parameter, from the parameter. And we can do nothing with this fact. It's just a fact. It's just all reality we have. Well, but if our statistic is unbiased, consistent, and efficient, if we know that, so imagine that we can conduct 100 trials, 100 surveys We can calculate 100 averages, and if we know that these averages, 100 averages or 1 million averages, should be concentrated around the population average, we can trust our statistic. Again, if we know that conducting many surveys using different samples, different individuals, persons, firms, gives us can give us different averages, different statistics, but we know that these statistics should be concentrated around the population parameter. We can trust our statistics, and we can trust all of our averages. We can trust even 4.6 average in our research, because anyway, this average is unbiased and consistent. What consistent estimator means? Well, if our estimator is unbiased, well, we can say that it is a consistent estimator if the difference between the estimator and the parameter tends to become smaller as sample size becomes larger. If we know that investing in data collection could increase our accuracy, could increase the accuracy of the analysis, we can say that our estimate is consistent. And by the way, if our samples, samples are larger, we can obtain narrower distribution. And in your textbook, you can find an illustration of this fact. Well, and vice versa. If your sample size is small, this distribution should be wide. Well, an efficient estimator means that there is no other way to obtain a more precise estimate, statistic. Well, and this is the second important fact, that we should try to get unbiased, consistent, and efficient estimators. And next, remember, during this course, keep in mind that all statistics we have are random numbers itself. Again, all statistics we have are random numbers itself. You can learn it from this exercise. And again, remember, learn it by heart. Write it somewhere. All statistic, averages, standard deviations, medians, modes are random number itself when we work with sample data. Hence, they can follow some distribution. Well, and we use this fact. This is a backbone. It is a base for hypothesis testing in statistics. And if you don't understand this fact, you will never understand why we need to conduct statistical tests instead of simple comparison of two or multiple numbers. Now, questions, because it is a pretty or probably the most important topic in this course. Questions. You can type questions in the chat, or well, if I'll write it clear or unclear, I can explain it again. All students being present in the lecture type clear or unclear, because it is this topic is extremely important. If you understand it, you will understand the whole statistics, okay? Right. Arina. What this phrase is like a dogma. But it's not a dogma for sure. You have to remember it. And I think that you shouldn't check it because we check it. No, by the way, yeah. I mentioned that if we use larger sample, you can get narrower distribution. If you wish, you can check it at home. No, now we don't have sufficient time. Only you can use smaller samples, you can check it, or you can use more samples. What if you use 1,000 samples? What will happen? Now, let me show you my exercise. I did it 1 year ago. I used here, let me show you. Well, yeah, look, this is a similar example when I have 100 surveys. Distribution is similar, it's bell-shaped, but so it doesn't look good. But if I use 1,000 of wait, yeah, if I use 1,000 surveys, look, my distribution is closer to a normal one, and more values are close to the population parameter. Wow. And if n is infinity, the distribution must be normal one. That's a rule. Well, Karina, yeah, that's a really good question. To be honest, second point, you should take into account other points. Yeah, for sure. Well, first, guys, remember that in practice, it's impossible to conduct 100 of 1,000 surveys using the same population. It's too expensive and doesn't make sense. We always conduct just a single survey, and that's a problem. We have just a single sample average, and we use our knowledge. Or today we discussed all of this stuff. We use this knowledge to think whether our sample average should be consistent, unbiased, and efficient, and whether we can apply and why we can apply different statistical tests. Well, does it mean that random nature of sample averages can tell us that anyway we can trust our numbers? No, there are other problems, and we have to discuss these problems later. For example, there is a selection problem, or there are measurement errors. So you can mistakenly measure something. Your sample could be representative, but because of measuring error, well, your results cannot be reliable. But technically, so your averages could follow a normal distribution. Well, so in short, Karina, answer to your question, you should take into account all the points. Well, Alina, I mean, in order to trust our statistics, we should check it how far is sample mean and parameter. Well, again, in practice, you cannot check it. It's impossible. You don't know population mean. You have just a single sample average. But you have to keep in, well, why we need to learn it? We need to learn it to justify why we need to conduct statistical tests, why we need to rely on different statistical tables. Well, if it is unclear now, just remember this theory. Just try to remember and understand how it works. And later, when we learn confidence intervals, when we learn hypothesis tests, I will show you we will often mention this theoretical concept. Well, okay, and the last point, let me tell you about stata. Unfortunately, guys, our website, our webpage about stata is in Russian. So what you have to do, you have to, well, if you are on distance learning, please download and install Stata 17 for HEC students. Here you can find instructions. Note that so our license expires on October 1st, and later HEC will provide you with a new license. Also, you can find Stata in our computer classes. If you need Stata in our computer classes, I think it is the easiest way to find it. Please contact Valeria Galchenko. She is in our dean. I think you know her. Well, she can help you to book a room. If I see that I'm in a computer class, so I teach something, you don't have to book it. You can just find any empty seat and work in Stata without any progressing procedures. If you see that I teach something in a class, okay? Well, we will work in Stata. Couple of words about Stata. Stata, one of the most popular programs in data analysis. It's though this is Stata, it looks like this, and we will use it a lot in our course. Well, why Stata? Why not R, not Python? First, Python and R both, in fact, they are programming languages. And in order to learn statistics with Python or RStudio, first you have to learn RStudio and Python. As far as I know, you haven't learned them. You haven't any course about Python or RStudio, hence we cannot use them. Another problem, well, Stata, so both RStudio and Python are free, in fact. And you know that quality of product and cost of product usually are correlated. So free product, low quality. And the same can be said about Python and RStudio. In Stata, it is a paid program, and it's a fairly expensive program. We have all we need. It is a very powerful and very simple, very intuitive, professional statistical software. Well, and if you think that Stata isn't, so now Stata isn't very popular in Russia, but its popularity is growing fast. You can check it visiting Headhunter website. You can type Stata there. Well, and you will see some vacancies requiring knowledge of Stata. Well, and also Stata is extremely popular abroad. If you want to work somewhere as a research assistant or somewhere in Europe, I am sure that you will have to use Stata if you want to work with statistics. Well, and fortunately, Stata is so simple that you can easily start working with Stata within 1 week. For example, when I was a student, I learned Stata by myself within 2 weeks without any teacher. It's so simple and it's very, very powerful. Well, our teaching assistants, we have 8 teaching assistants. They will help you to download, install Stata and to check that everything works well. Well, they can consult you with Stata, and today I will provide you with their emails. Probably you know some of the students. Well, they could help you. Please be very polite with your teaching assistants and know that they are also students. They are also learning to communicate with another students, to solve maybe some problems. Take into account this and be very friendly with our dear teaching assistants. Well, by the next seminar, you have to install Stata and be ready to work with. And now let me show you one simple thing about Stata. Let's open one data set. Well, this data set is about car sales. Well, 1 week ago, I spent maybe So 2 hours to explain how to calculate means, medians, and so on. In static, this can be calculated using a simple short command. Summarize price variable in detail. And look, let me show you. And look, static calculates median, average, standard deviation, variance, skewness, kurtosis, sample size, percentiles, first quartile, third quartile, for smallest, for largest values. It calculates everything within 1 second. Well, it's very simple, it's very powerful, and we use it a lot in this course. Questions? Okay, what have you learned today? Type in the chat, please. It's a form of checking your attendance, real attendance. Oh, thank you, Georgi. Static operation would be very thank you. But what about other things? Safum, what does it mean? Chebyshev theorem, okay. Transpose, not bad. Statistical measures are random, good. Sampling error for mean. Sampling error for mean. Run. Absolutely, you're absolutely right. Yeah, Karina. And other students, please remember that. So in statistics, there is one tricky point. Machine, state or Excel or Python R, they can always calculate something. They can always provide you with numbers, charts, tables. But it doesn't necessarily mean, it doesn't mean that you have to trust these outputs. And whether you have to trust makes statistics more closer to art than pure science. Okay, okay, so dear all, thank you for your attendance. Have a nice week. See you next week in seminars and in the lecture. Please install Stadia by the next lecture. Don't try to install it next, so before the lecture in the morning. Please do it in advance. That's it. Thank you very much. See you. I stop the recording.